Prasad, good evening. Hi guys. Hi, good evening, Anusha, Chinmay. Mhm. Yeah, guys. So let's wait. Meanwhile, please take the technical check, guys. Let me know if my voice is audible clearly and if my screen is visible clearly. Okay. So then I have a small. So let's check our class. Yeah. Hope everyone has come prepared to the class, guys. Yeah, don't worry. We will try to go as slow as possible. We won't go in a hurry as discussed. We will be in a normal phase. So if you feel a hurry somewhere, please let me know. Yeah, let's try to complete the syllabus, guys. That's the only thing. So our exams are nearing right. So we have to complete the syllabus. So we have to be in a bit. We have to speed up a bit, but it should not be like it should not be more like rushing, but should be speed up more than normal. Okay. So I hope everyone is able to hear my voice clearly. Yes. So I see. So we don't have enough time, guys. Please be on time. Hi, Krishmodi. Hi, Hariprasad. Hi, Bhargav. It was great. Okay, cool, guys. Super. Thank you. So here, I'm waiting for more guys to arrive here. So let's start our revision. Okay. So I'm going to end the poll, guys. Yes, my voice is clear, and everyone is able to hear my voice clearly, and the board is visible clearly, right? Cool. So I'm going to end the class. End the poll here. I'm going to end only the poll here. So we'll start the class now. Okay. So yeah, in our previous class, we had discussed about the basics or the introduction of the current electricity, right? So we learned about. Can anyone brief me what we studied in our previous class? So what are the things we discussed in our previous class? So please reply, guys. Your reply is very, 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 very much important. So what was the first topic we discussed about? So what was the very first topic we discussed about? Meeting. Please reply, guys. So we started with something called as conductors. What are conductors? So conductors are those. What are conductors? Conductors are materials which allow free flow of electrons. Right? Okay, I can't say electrons. I can say free flow of charges. Okay, free flow of charges to pass through them. Those are conductors. So for conductors to conduct, what I wanted, say if I have a conductor, say there were n number of n number of atoms in the molecule of conductor, and each atom, say if I consider a copper conductor, if I consider a copper molecule, so each atom contributes at least one electron, right, from the valence orbital at room temperature. At room temperature, my room temperature is enough for this electrons to move out. So this is the isolation energy which we discussed, right? So this amount of energy is required. Amount is enough for these electrons to move out of the atoms. Now, when they move out of the atoms, will they stay in a place, guys? Will they stay in a place? Will these electrons which move out from the valence orbital or valence shell, will they stay simply in that position at room temperature? Guys, reply, come on. Please reply, guys. Your reply is very, very, very necessary. No, they won't stay in a place, right? Yes. Okay, cool, Arif. Thank you, thank you. Thanks for picking up. So next, what we did, so we took this conductor and we connected a potential to this conductor. Say if I consider, so yeah, at room temperature, there were free electrons formed. Now I'll take this conductor and I'll connect a potential to this. What happened? So I connected a potential difference to this. What happened to the conductors? Or what happened to the electrons inside the conductors or charges inside the conductors? What happened to the charges inside the conductors? Or what happened here exactly? So there was a current I which was in this direction, right? So there was a current flowing in this direction. So there was setup of an electric field inside the conductor. Now, what is the direction? What are the two types of current we know? So we know two types of current, right? So one is proton current or positive current. So flow of positive charges. So this is also called as the conventional current. Okay. And yes, other one is electron current, right? Electron current. So this is the flow of electrons. So flow of electrons will be opposite to what? Opposite to conventional current. Okay. Okay. This is what we studied. Then we know the expression for current. So the expression for current for any given instance is given by I is equals to change or the amount of charges flowing for unit time. So this was the expression which we learned for calculating current. So current is nothing but amount of charges flowing for given unit time. It's always unit time. So this what is the Q value we have to consider here? Here the Q value should be, what is the Q value? Q net. It should be the Q net. So Q net was given by total amount of positive charges flowing minus total amount of negative charges flowing inside a conductor. So this was the net charge flowing inside a conductor. So rate of charge. So the current was given as rate of flow of charges, right? And SI unit of current was, SI unit was amperes. This amperes denoted by capital A. Next, we learned that I. So now my I would be given in this condition. So what will be my I? Current I will be given as, so total of positive charges minus total negative charges divided by T. So this was the current expression. So this can be again rewritten as, so what is my I? I is nothing but change in current. So I is nothing but change in current for small instant of time. So I is equal to delta Q by delta T. Say if I consider only the small unit of time. Now, if my time tends to zero, the amount of changing flow of charges for small instant of time was given as current. So this was written again. When I had the limit condition, it was written as dq by dt. So this was the thing of not small bits, again still the same cap and Q charge. So this was the expression for current which we got. Next, we derived an expression for current, say stating if I consider a conductor again, if the conductor consists of Q amount of charges, Q net amount of charges, this Q net amount of charges can be written in terms of number of electrons or number of protons into elementary charge times area into drift velocity, right? If you remember, this was given in these terms. Now, what is drift velocity? So we learned something called as drift velocity. What is drift velocity? So the velocity with which the electrons move inside a conductor. Yes, Ramakrishna Reddy Hari Prasad Subbottam. So the amount of, so the velocity of electrons or the velocity of charges inside conductor is called as drift velocity. So we had derived an expression for drift velocity, and the final expression was given by Vd is equals to E times of E by M into tau. So we had a brief, yesterday we had discussed how this derivation came. So we considered force acting on the charge because of electric field, which was set up here, and the mechanical force acting on that charge was given by A is equals F is equals to ma. From there, we got the acceleration. From acceleration, you by substituting the value in the kinetic relation. Finally, kinematics equations relation V is equal to U plus AT. We got this expression Vd is equal to E dot E by M into tau. So this was again the drift velocity with which my electrons moves. So then the current in terms of drift velocity was given by number of electrons or elementary charges moving for a given area times Vd, drift velocity. This was the expression I is equal to NU Vd which we got. Then the current density should negative should be okay. Yes, Vd was given with a negative sign because if this is considered as an electron, so Vd gets a negative sign only if this is considered as an electron. So yeah, if my charge was an electron, then Vd gets a negative sign. If my charge was a positron or a positive charge, Vd will get a positive charge. If charge was negative electron, then Vd will get a negative sign. Okay. So that's how the sign varies. But in general, Vd is given by E dot E by M times of tau. Okay. Next, guys. Yeah. Next, we studied about current density. What is current density? Current density is nothing but J is equals to I by A. Right? J is equals to I upon A. So when we try to substitute the values of I and A, we got J as J is equals to N E square E by M. Right? N E square E by M times of tau into Vd. So sorry, this is the one N E square E by M times of tau. This was the expression which we got. So what I did, I substituted the value of Vd here and multiplied it. That's it. So this was the expression. Now this constant, this is a constant. This is constant is called as conductivity. So this constant was called as conductivity and it was given by sigma. The symbol given was sigma. So the inverse of conductivity is rho, that is resistivity. So resistivity is the inverse of conductivity. Next, finally we studied about something called as mobility of electrons. So mobility of electrons is it says about how much free my electron is to move. Mobility of electrons means it shows how much free is my electron to move inside a conductor. Okay, so it's given by the drift velocity upon electric field, or drift velocity per unit electric field is called as the mobility. So this in terms of expression we write it as mu is equals to E times tau by M. Okay, so I can say my E and M are constant, so mu is directly proportional to tau. So yesterday we discussed this. If my electron takes very short duration of time to collide with another atom, then the mu is very less. If my electron takes more time, then magnitude of drift velocity upon electric field, right? That is mobility. So if my electron takes more time to collide with another atom, then my electron has enough space in the region to move. So this is my mobility. So guys, whenever you get a chance to write, so entire chapter should be written in one single page. Okay, one single page, or you should at max write in two single page. So you could remember all the everything which we learned in yesterday's class is covered in one single page. Okay. Likewise, you could also try to write if you know the flowchart, if you know any simple form. Yeah, if you know any simple way to remember all the points, make point wise or flowchart wise and remember. Okay. So this is what we learned in yesterday's class. In today's class, we'll be starting with Ohm's law and resistivity. Guys, please reply. Hope you guys have understood yesterday's class. So yesterday, I hope most of you might have went home and revised again. Did you guys do that? If not, please do that. Please revise that. Yesterday's topic was very, very simple and it was easy. Okay. So today we'll be coming to Ohm's law. So what happens? Who is this Ohm? Ohm. Okay. So this guy, Ohm. So Cool, guys. So there was one guy called Ohms. So what he did, so I don't know his full name. So what he conducted an experiment. So he observed Ohms was very curious about the conductors. So what he did, he took some random conductor. So he took a random conductor. Now he connected this conductor to a battery. Okay. Now in the path, so he connected an ammeter here. So in the path of this current, he connected an ammeter and he measured the voltage across this conductor. Okay, so this was the experiment which was conducted by Ohm. So what he did, he varied. Sorry, I can't write E, I will write V only. So he varied the applied potential. So he varied the applied potential and saw that for same amount of potential, the current was varying. So for different conductors, the same amount for the same amount of voltage, for the same amount of voltage, my current was varying. For same voltage, current was varying for different conductors. For different conductors, my current varied in different way. So this he checked. Okay, can I check? So whom thought this? Okay, can I check? Can I apply for various conductors? So this is a conductor. So I'll take a different conductors. So I'll take copper one time. I'll take aluminum one time. I'll take gold one time. Okay, why copper, aluminum, gold? So I'm not so rich. I'll take iron, or I'll take other steel, or I'll take nichrome. Okay, chromium. All these. So he took different samples of conductors and followed this same experiment. Now, at last, he came to a conclusion. So this conclusion, so he publicized. See what happened is Holmes publicized this observation. This observation only he publicized, but later people took it as Ohm's law. Actually, did not give any law, but he gave only his observation. He observed some peculiar thing which was happening in a conductor. He was conducting an experiment. In that experiment, he observed a peculiar thing. So it was a unique thing. So he found that something new. So he published that in the entire community of science. Then, yeah, this today we have showing it as Ohm's law. Okay, so what are we going to learn today? We will be going to learn about Ohm's law. So Ohm's law had some limitations. So we'll be learning about limitations of Ohm's law. Then we'll be learning about resistivity of materials. So yesterday we learned that conductivity. Conductivity is how much my conductor can allow the free flow of electrons. So we learned that resistivity is nothing but inverse of conductivity, or conductivity is nothing but inverse of resistivity, or resistivity is nothing but inverse of conductivity. In yesterday's class, we learned this. So we learned in detail about how resistivity varies for various materials. Okay, then we'll learn about a simple material called as, some simple device called as resistor. So we'll learn about the simple device called as resistor. So why resistor is required? What is the significance of using resistor? We'll learn that. Then we'll learn about color coding. So resistor as a device, we'll get in market, we'll get resistors. Most of you might have seen those in your circuits, many of your broken circuits which you might have broke. So you might have seen that, but you may not know what is that. So today we'll learn about a resistor, a particular type of resistor, one type only. So we'll check that. So I'll try to give some brief detail about other types of resistor if time permits. Then we'll discuss about temperature dependence of resistivity. So how my resistance varies as my temperature varies in the environment. So we'll discuss all about this, and why should we discuss? We'll discuss that too. Okay. So let's start with Ohm's law. So what happens? Ohm's law. Ohm's law states that, say if we consider a conductor, so Ohm's what he did, I told you, as I told you, he considered a conductor of length L. Now, this conductor was connected to a potential difference. So first what he did, he considered a conductor of one length L, same length L. Yeah, yes, he considered a conductor of length L. Now he applied a potential difference of voltage V. Now what happens? There exists a current, right? There exists a current inside the conductor from positive terminal to negative terminal. So we learned that it's the conventional current. Now, is there any relation between the potential applied and the current? So I observed. So as we discussed earlier, so what happened? Depending on the material of the conductor, so depending on the material of this conductor, my current for the given potential varied. Okay, the current for the given potential varied. So this is called as, so he observed that and he documented that. This was called as Ohm's law. So yeah, That is given by, so there exists an electric field. Now, if the physical state such as the length, temperature, pressure, etc. of a conductor remains constant, say if you consider the parameters, physical parameters such as length, the temperature of the conductor, and pressure also. So standard temperature, pressure, you might have learned this in your chemistry. So if the physical states of length, temperature, pressure, etc. of a conductor remains constant, then the current through an ideal conductor, so and the current through an ideal conductor is directly proportional to, or yeah, proportional to the potential difference across it. So the current, then the Ohm's law can be given mathematically as I is directly proportional to V. Guys, this is very, very important. My current will only depend on voltage. Okay, voltage does not depend on current, but my current will depend on voltage. So I is directly proportional to V. Okay, this is the way you have to write. So the Ohm's law states that for given standard temperature and pressure, the length of for a given standard temperature, pressure, and length of a conductor, the current flowing through a conductor remains constant, or the current through an ideal conductor is proportional to the potential difference across it. So I is directly proportional to V. Now, how much is it equivalent to? So if I try to remove the proportionality constant, I'll get a new term. I is equals to V by R. The current flowing through resistance varies, or yeah, is equals to V by R. The applied potential by the resistance. So we have the new term R. This is called as the resistance of the conductor. So what is resistance? So guys, what is resistance in general? This is called as a resistance of conductor. So what do you mean by resistance? Please reply, guys. Guys, please reply. What is mean by resistance? I think we discussed in yesterday's class when I was discussing about resistivity. I told you about resistance. What is resistance? So how does this resistance exist in first case? Guys, please reply. Come on, guys. Yes, resistance means opposition. Okay, resistance means opposing or opposition for free flow of charges. Okay, flow of charges. Okay, now who is opposing this? Who is opposing this? Is there someone who is opposing the free flow of charges? So this is my resistance. Resistance is nothing but opposition for free flow of charges. Now, where did this resistance come from? So, guys, as we know, the conductor consists of n number of molecules, and n number of molecules consists of n number of electrons, right? So when we apply a potential, what happens? So when we apply a potential, a positive current flows in this direction. My electron starts to move in opposite direction, right? So yeah, my electron starts to move in opposite direction. So it will start to move in this direction. So in its way, it will start to collide with another electron or an atom, then starts to collide with the other atom. So what happens? It's not flowing very freely. It's not flowing very smoothly, right? The package of the conductors, say inside the conductor, there are n number of atoms. These electrons collide on each atom. So when it collides on each atom, what happens? There is resistance, there is opposition for free flow of this charge. Okay, this opposition for free flow of charge was called as resistance. Yes, Rakesh. Rakesh, please. Yeah, please ask. Okay, guys, please text now. Rakesh, please ask your doubt. You have raised your hand. Any doubts? Guys, please text. Guys, please try to answer. I mean, try to send some message. Okay. Okay, cool, guys, cool. Okay, chat was, yeah, chat is enabled. Rakesh, I think you are able to answer now. Okay, cool, guys. Yes, Kriti, you have any doubts? Please ask your doubts. Kriti, if you have any doubt, please ask. Okay, cool. So, what was resistance, guys? Okay, all this time it was blocked. I don't know how it was blocked. Okay, cool, guys. Sorry for this. Okay, now it's enabled. Sorry for the disturbance. Yeah. Cool. So resistance was the opposition for free flow of charges. So how did this resistance occur? So when my electrons are trying to move in the direction of electric field, so there was electric field, right? So there was electric field in this direction. Now my electron starts to move. Okay, say it moves in some direction. Now there is opposition for flow of these electrons. Now this opposition for free flow of electrons or free flow of charges is called as resistance. Okay, so this is how there exists a resistance inside this conductor. Understood, guys? Who is giving the resistance? The conductor itself. So, what are pure conductors? What are very good conductors? What are very bad conductors? So here is the reason. So what happens in pure conductors? Sorry, in good conductors, what happens? The electrons can flow freely. So that is the only difference between a good conductor and a bad conductor. Okay. So electrons can flow freely inside a good conductor, whereas for bad conductors there will be lots and lots of these obstructions, maybe because of their package. I hope you guys have studied about atoms package in your 11th standard. So how they are packed. So yeah, you might have learned the bodies in the cube, place in the cube, etc. Like those, right? So on those spaces, I hope you guys know about voids, which was taught in your 11th chemistry. So there will be free spaces in between the atoms. So these free spaces are the paths where my electrons can move. Okay. So if there are no free spaces or less free space, then the resistance will be more. If there are more free space, then the resistance will be less. So V is equals to IR is the expression for the relation between voltage and current is given by V is equals to I into R. So this was given by Ohm's law. So I is directly proportional to V for given physical constants, say for the length, temperature, and the pressure for a given standard length, temperature, and pressure of a conductor. The current flowing through the conductor is directly proportional to the potential applied across it. So it is given by I is equals to V by R, V or V is equals to IR, where R is called as the resistance of that conductor. Okay, so this is Ohm's law, the definition for Ohm's law. So and above is the statement for Ohm's law. Okay, now yeah, the alternate form of Ohm's law. So we had studied that there exists the current density. I hope most of you might know what is current density. So yeah, so we have something called as the current density. The current density is given by J is equals to I by A. From here, we are going to derive an expression for resistivity. Okay, we are going to derive an expression for resistivity. So what is resistivity, guys? Again, resistivity is a material property. Okay, resistivity is a material property. This shows how much is my resistance for any given conductor. Okay, resistivity is a material property. Now the resistivity is, so there are two types which we can explain the same thing. So the resistivity depends on, so the resistance. Okay, let's come to resistance. The resistance of the conductor. So what are the factors my resistance of the conductor depends on? So the resistance of any conductor depends on few geometrical aspects or geometrical properties, such as the resistance is directly proportional to length of the conductor. So length of conductor. Okay, and the resistance is inversely proportional to the area of cross section of conductor. Okay. No other ways to represent. We have to change the conductor. That's it. Then the resistance, we can write resistance is proportional to length by length upon area. So this, if I equate it, I'll get a constant that is called as rho. So this rho, whatever we get, is called as resistivity. Okay, this rho is called as the resistivity. So it's a materialistic property. So it depends on conductor, type of conductor. Yeah, it depends on nature of the material. So if a material is highly conductive, then resistivity will be very low. If the material is weakly conductive, then the resistivity will be very high. So we know that from yesterday's formula, we know that if we try to simplify, so this is the alternate form of Ohm's law. So in your CBSE syllabus, they would derive this expression first, then arrive at this expression. So yeah, what happens? Say if you know R is equals to rho L by A, then if this is called as resistivity, in yesterday's class we learned that Inverse of resistivity is called as conductivity. What is my conductivity? It's the inverse of resistivity. Now again, you know J. So we'll come in the ulta way. So we know the current density is given by J is equals to I by A. J is equals to sigma times of E. Okay. So this is the alternate form of Ohm's law. So where the current density is equals to conductivity times of electric field. Okay. Now J is nothing but I by A, that is equals to sigma times of V by L. So we learned that electric field inside a conductor is nothing but E is equals to V by L in this class. So we are just applying all those. Now we know that I by A. So from Ohm's law, we know that V is equals to I into R, right? From here, if I try to rearrange, so if I keep my V potential on one side and move all the other constants on the other side, I would get this expression V is equals to I into L by sigma times of A. Now this L by sigma times of A is equal to, this is similar to, we know that from Ohm's law, V is equals to IR, right? We know from Ohm's law, V is equals to IR. Now my R is equals to L by sigma times of A. Now if I try to rearrange this, so my R is equals to L by sigma times of A. We know that 1 by sigma is nothing but my rho. So I'll get the expression R is equals to rho L by A. Okay. This is, yeah. So this is the resistance expression. So this is the alternate form of Ohm's law. So in your CBSE syllabus, you would have gone in the opposite way, but here we are explaining like this. So in yesterday's class, we learned that the current density is nothing but current per unit area is equals to sigma times of electric field. The electric field was given by V by L. Okay. Okay. Now, okay, we get V is equals to IR from Ohm's law. So on substituting the value V is equals to I into L by rho A, sigma A, that is I into R. My R will be L by sigma A, that is on rearranging we get R is equals to rho L by A. From here, yes, we can derive the expression for rho. Rho is equals to, from here we can write, if we keep rho here and move all other things, then we'll get rho is equals to RA by L. Okay, this is the expression for rho. We can derive that. Now, where rho is the resistivity, okay, where rho is called as the resistivity. So, yes, L by A, rho is equals to, so R is equals to L by A. So this was my resistivity. My rho is nothing but 1 by sigma. So in yesterday's class, we know that sigma was nothing but N E square tau by M. Guys, if you know, the conductivity was given by N E square tau by M, which we revised, right? So the 1 by, if sigma is equal to N E square tau by M, then my rho will be obviously 1 by sigma, that is M by N E square tau. Okay. This was the other expression for rho. Okay, rho can be calculated either this way, RA by L, or with these terms M, N, and E square and tau. Okay. Yes, resistivity is a materialistic property. Cool, guys. So this was about resistivity. Next, yeah, where L is the length of the conductor. Okay, where L is length of the conductor in the direction of current, and area is cross section of conductor. Next, we have a problem based on that, guys. Please try to solve. Okay. So find the resistance of an aluminum wire of length 50 centimeters and area of cross section 2 millimeters square. If the resistivity of the aluminum is 2.6 into 10 power minus 8 ohm meter, please try to find the value of its resistance. Guys, please try to find the value of R. The options are given here. Please try to find the value of R. Be quick, guys. Find the resistance of an aluminum wire of length L is equal to 50 centimeter and area of cross section is 2 millimeter square. If the resistivity of aluminum is 2.6 into 10 power minus 8 ohm meter, find its resistance. R is equals to, guys, please use the formula. So we know that R is equals to rho L upon A. Substitute the values and find the values, guys. Come on. Guys, we are running short of time. Please be quick. Okay, some of the answers are being available. Are you able to answer the poll, guys? I think poll is launched, right? Hope poll is launched. There might be no, there might be no problem in answering the poll. Yes, cool, cool, guys. Yes, correct, Tejas. Superb. Okay, guys. So please try to answer. Okay. Now let's check the answer. The answer is, yeah, most of you have answered option C. Yes, option C is the right answer. Okay. So let's check how it's done. So we know that if we consider a conductor of length L, so the L is given as 50 centimeter. Okay, L is 50 centimeter and area of cross section of this length is A is equals to 2 millimeter square. Now the rho, we have to find the rho is given as 2.6 into 10 power minus 8. From here we know that R is equals to L by A. If we substitute the value of rho is 2.6 into 10 power minus 8 and L is 50 centimeter, that is 0.5 meter, and area of cross section 2 millimeter square, that is 2 into 10 power minus 6 meter square. On substituting the values, we get 2.6 into 0.5 by 2 into 10 power minus 8 by 10 power minus 6. So on simplifying, we will get R is equal to 0.0065 ohms. Okay, so this is the expression, this is the value. Okay, hope everyone have got this. Yes. So next we have another, another question similar to that. So given is a hollow cylindrical conductor. Say I have a hollow cylindrical conductor of area of length L is equals to 1 meter. So this entire length of this conductor is 1 meter, and the outer radius. So this cylinder will be having, okay, it's a hollow cylinder, right? So it has two radius. So outer radius is about, so inner and outer radius. Inner radius is about 1 meter, and outer radius is about 2 meters. Now find the resistance along the length. Given the resistance, the resistivity of material rho is 2 into 10 power minus 8 ohm meter. Please try to find the value, guys. What is the area of cylinder, guys? Area of cylinder. Area of cylinder. Area of cylinder is given by. So please consider there are two cylinders. Subtract the bigger cylinder area minus smaller cylinders to get the hollow cylinder area. Okay, guys, how to solve this? Subtract the bigger, find the area of two cylinders. First, find the bigger cylinder radius. First find the area of bigger cylinder. Area of big minus area of small cylinder to get the area of hollow cylinder. Area net. Okay. Yes, pi r square. So is it 2 pi r square or pi r square h? Which one is the formula? So which area I require? Which is the area I require? Is be specific about the formulas, guys. It is A is equals to pi r square h. Yes. Yes. Please use the formula. A is equals to area. Correct, Pradeep. Area of cylinder is equals to pi r square h. Please try to substitute the values and find the expression, guys. So I'm quickly launching the poll for you guys. Please try to answer the poll. And others, please try to answer. Yes, Mother, correct. Guys, please be quick. Please be quick. Yes, still waiting for the answers, guys. Okay, cool. So yes, Tejas. Yes, this is correct answer. Tejas, right answer. Others, please try to give the answer, guys. Come on. Come on, guys. Come on, come on. Please try to be fast. So yeah, there is a reason why we have to rush. I don't want to rush, but if you guys be very slow, that I have to rush. Okay. Yes, cool, guys. So I'm going to end the poll, guys. Yeah. So answer is yes. Correct answer is option B. So most of you have given this answer. So how to solve this? So to solve this, we know the area of cylinder. So we have to find the area of bigger cylinder first. That is pi r square h. So what is my r square? 2. 2 square is 2 into 10 power minus 3 meters whole square into 1 meter. Right. So this is my area, bigger area. So what is the area of this, guys? This should be somewhere around 4 pi. Yes, 4 pi millimeter square. I'll keep it as millimeter square only. Then area of small should be equals to 1 pi millimeter square. So what is my net area? Net area, A net. A net is equals to 4 pi minus 1 pi, that is 3 pi millimeter square. So this is my area. Yes, cool. Now next, guys, please try to simplify that. You know, rho is equals to R A by L, or yeah, what we were finding resistance, right? So we, R is equals to rho L by A. So on substituting the value 2 into 10 power minus 8 into L is 1 divided by A is 3 pi into 10 power minus 3 meters, right? Okay, it was millimeter square, so into 10 power minus into 10 power 2. So it was square, right? So yeah, we'll try to simplify this. We will get 2 into 1 by, okay, it's 2 by 3 pi times into 10 power minus 8 into 10 power plus 6. So you would get 2 by 3 pi. So what's the value, guys? You will get on simplification, you get 2.1 into 10 power minus 3 ohms. Okay. Please try to simplify in your range time. So this is the expression. Okay. Yes, guys. Okay. Yeah. Yes, guys. Got this now? Marg, which is volume? Pi r square, right? We are doing pi r square. Is that volume? No. Okay. Next, guys, let's go to the next concept. So there was one more question, guys. Please try to solve this. So the resistance of a conductor of length L and cross-sectional area is A is R. If the length is made twice and cross-sectional area is half, then find the new resistance of this conductor. What is the new resistance of this conductor? Guys, please note this. This is a very simple question. Say if the resistance of a conductor. So we know that R is equals to rho L by A, right? R is equals to rho times, yes, correct, just rho times L by A. Now, what is happening? If my if the length is made twice, if L is increased by 2 times, L into 2, and my area is reduced by half, how much is the new resistance? R new. Please reply. Yes, correct, Krishmodi, correct, Tejas. So we'll check the length. So let initial length be L, then the area of cross section be A. Now the rho resistivity of the initial resistivity is given, or initial resistance is given by R is equal to rho L by A. Now what happens? So if the length is doubled, so length L dash is 2L, and the new area is reduced by half, so A half. Then now for the same resistivity, we get the new resistance as R dash is equal to rho L dash by A dash. So that is rho times of 2L by A by 2. So on simplifying, you get 4 times of 4 times of rho L by A. So this rho L by A is nothing but my resistance. So R dash will be equal to 4 times of R. So on increasing the resistance and decreasing the volume, on increasing the resistance and decreasing the area, we get the net resistance increases. Okay, the resistance increases on increasing area and decreasing volume. Okay, so I have one more question, guys. The resistance of a 10 ohm, sorry, I'm launching the poll, guys. Yeah, the resistance of a material the resistance of a metal rod of length 10 centimeter and area of cross section is 1 centimeter by 2.5 centimeters. So this is a rectangular, yeah, this is a rectangular conductor or a metal of length 10 centimeters. Okay, and so if you assume a rectangular bar, okay, you get something like this. So this is half centimeter and this is 1 centimeters. So breadth is half centimeters and length is 1 centimeters and height is 10 centimeters. Okay, you could take Bhargav, yeah, please listen, Bhargav. See what's happening. It's the same similar question. So we know initial length was L. So initial resistance and initial area was A, Bhargav. So R is equal to rho L by A was the initial resistance. Okay. The initial resistance on calculating we get R is equal to rho times of L upon A. Now what is given in the question? My length is increasing. If length is increasing twice and area of cross section is reduced by half, so length increased by 2 times and area reduced by half times. So my new length is 2L, new area is A by 2. So on substituting the value, we get rho times of 2L by A by 2. So on substituting all the values, we get 4 times of rho L by A. So this is R dash is 4R. Okay, that's how we get. We'll discuss about that, Bhargav. We'll move on. Okay, we'll check that in the end, or please contact me later. Okay. So yeah, so the resistance of a metal rod of length 10 centimeters and rectangular cross section of 1 centimeters by half centimeter is here. Now, when the battery is connected across 1 centimeter by which of these cases will my resistance be maximum? When will I get the yeah? When will I get the maximum resistance? Okay. Yes. We'll discuss about that, Bhargav. Please contact me later. Okay. So when will the resistance be maximum? I have launched a poll, guys. Please try to answer this question. So yeah. Cool, guys. Superb. So I'm getting answers. Nice. Please try to check that answers, guys. Come on. So yes, Tejas. Now it's correct. Rakesh, correct. Initially it was error. Now it's correct, Tejas. Rakesh, correct. Here, please, guys, reply to this question. Reply. No, Bhargav, check your answer. Krishmodi, correct. Guys, please be very quick. Please be very quick. Yes. So what's happening here, guys? Again, it's the same application again. So option A is the correct answer. Okay, I'm going to end this poll. Yeah. So most of you are given B, but answer is option A. Okay. So option A is the right answer. Why? Why is option A correct? So please apply this formula. R is equals to rho L upon A. So guys, now my resistivity for all these cases, resistivity remains same, right? Resistivity remains same. Now let's check the first case, A case. In A case, my length is 10 centimeters. Length is 10 centimeters. Okay, area of cross section. So what's happening? Maximum when the battery is connected across 1 centimeter by half centimeter faces. So my battery is connected across this. Okay. Now, where are my battery connected? So it depends on when the maximum when the battery is connected across which are the two phases where my battery should be connected, so that I'll get the resistance of middle rod to be maximum. Yes, thank you, Hariprasad, for the clarification. Yes, guys, come on. Yeah, option A is the right answer, guys. So here, what are we going to check? So please check this. So what's happening here in this case? The resistance, the conductor is connected with across the area, right? So when the battery is connected across 1 centimeter and half centimeter faces, So this is 1 centimeter and half centimeter phases. Here, when my battery is connected, the resistance was maximum. So how? So maximum when the battery is connected across. Okay, which one of the options is correct, guys? Come on, yep. Let me know in the chat box. Guys, please answer this. Answer this question. Yes. So the resistance of metal rod of 10 centimeters and a rectangular cross section of, so the cross section is 1 centimeter by half centimeter. So maximum when the battery is connected across 1 centimeter and half centimeter faces. This means the battery is connected here in this face and this face only. Okay, the battery should be connected in this faces. So these are the faces. Okay, so how many face does my rectangular has? Sorry, how many face my rectangle has? Say if I draw a rectangle, so it will be a cuboid, right? I'm not wrong, please correct me if I'm wrong. So it will be a cuboid. How many faces will it have? 1, 2, 3, 4, 5, 6. 6 faces, right? So which are the two faces? So maximum when the battery is connected across 1 centimeter by half centimeter phase means this phase and this phase, okay? So wherever I have shaded, these two are the phases where I'm connecting the battery. Option A means this. Option B means, so I'm going to take a different color. So when maximum when the battery is connected across 10 centimeter by 1 centimeter phase. So 10 centimeter phase is this and 1 centimeter phase is this. So if I connect this and this, will the current be maximum? Sorry, will the resistance be maximum? If I connect the top and bottom position like this, if I connect the battery here, will it be maximum? This is option B, okay? Option B says this, option A says this, option C says, okay, option C says this, okay? Option C says this, connected sideways. So this is option A, option B, and option C. Which one is correct? So option A will be correct. Since my length is maximum, okay, since my length is maximum and area is minimum, my resistance will be maximum at option A type connection. Okay, not B type, not C type. I hope understood, guys. Everyone have understood this. Hope everyone have understood this. Please click on S. Okay. Please let me know if you have understood this, guys. Come on. I don't have. Yeah. Come on, guys. So we have limitations of Ohm's law. So the Ohm's law, V is proportional to I, ceases to exist for certain cases. In which cases does it cease to exist? So you guys know in which cases the Ohm's law can't obey. The Ohm's law is not obeyed in cases of semiconductors. So whenever we have semiconductors, instead of conductors, whenever we have semiconductors or any conductor which shows semiconductor behavior. Okay, so why semiconductors behavior? So by now, guys, you might have learned semiconductors. If not, yeah, if not, please listen. So if not semiconductors, so if you have not learned semiconductors, please listen. So what happens? So in semiconductors, we have devices such as transistors and diodes. So this is a diode, and I have one more device called as a transistor. Okay, so we'll learn about this in semiconductors chapters. Maybe transistor is opted out of your syllabus, but you will be learning about diodes. Diode is a special device, semiconductor device, which blocks current. Okay, which allows only one way flow of current, and it blocks current in the opposite direction. Okay, you have a positive current. This device called diode will make the current move in only one direction, and it blocks the current in opposite direction. So for such devices, we can't apply Ohm's law. Okay, I hope you are following. Say Ohm's law states that for any given conductor, for the given applied potential, the current should also be proportional. So according to Ohm's law, my ideal conductor should follow this blue line. But what happens in practice, my conductor sometimes follows this condition. So it won't follow the blue line, it will deviate from the path. So my voltage ceases to be proportional to I in some cases. One such case is semiconductors, and second such case is heating coils. Say when if something is getting heated up soon. Okay, generally if some of the conductors are getting heated up soon, yes, if some of the conductors are getting heated up soon, then those conductors does not obey Ohm's law. Okay, so the relation between V and I depends on the sign of V. So yes, as discussed this will be discussed in your diodes or semiconductors chapter. This is the VI characteristic of a diode. So how if my voltage is increased? So in case of diode, if you have studied by now, if you have studied about the diode, it's very simple. Otherwise, we'll be studying about diodes in semiconductors chapter. So what happens? Diode, since diode is a unilateral network, it blocks current, it allows current to flow in only one direction, and it blocks all current. So if you remember, see this current is entering here and exiting, whereas this current cannot enter here. So it blocks current in one direction. So such networks are called as unilateral. So such devices are called as unilateral devices. So diode is one such unilateral device. This diode does not allow free flow of current in one direction. So it allows free flow of current only in one direction. For these cases, we can't apply Ohm's law. So what happens inside a diode? So the diode also, up to certain voltage, it does not allow the free flow of current even in one direction too. So there is some required amount of voltage, minimum voltage required to increase. So to make the current flow through this diode. Okay, that we will be studying in detail in the semiconductors chapter. Also, in reverse direction, when same amount of potential is applied, the current flowing through the device is very less compared to that of any normal conductor. In such conductors or in such semiconductors, we can't apply Ohm's law. So this is where my Ohm's law fails to satisfy. The relation between V and I is unique, and there is more than one value for V. Say in case of gallium arsenide, say this is in your LEDs. Okay, you know the light emitting diodes. There is a special diode called as light emitting diodes. So yeah, we'll be learning about diodes in detail. So diode is the two junction semiconductor device. So as I discussed earlier, so this diode is say semiconductors are those which have the conductivity between, yes, the semiconductors are those which have the conductivity between insulators and conductors, right? So diode is a special case of semiconductor device where it allows free flow of current in only one direction. Prasad, I hope I have explained that thrice by now. Please listen. So gallium arsenide, yeah, gallium arsenide is one such semiconductor where in the positive end I have gallium and the negative end I have the arsenic. So these gases are forming the LED light emitting diodes. So what happens in this? So current for any given voltage, the current will not be same throughout. Okay, there exists some negative current in semiconductors. We'll study about these also in semiconductor chapter. But I'm just giving a brief introduction. This is where the Ohm's law is not satisfied. Okay. Next, we'll learn about resistivity of various materials. So we learned about resistivity. So there is, yeah, we know that resistivity of any material is given by rho is equals to RA by L, or what was the other formula? M upon NE square tau. Right. So you guys remember both the formulas. Rho is equals to RA by L and rho is equals to M by NE square tau. Please remember both the formulas for this. Okay. Now these are the two equations which we know for resistivity, and I have some list of resistivity for different conductors. So always my resistivity varies in the order of millivolts or milliohms. Okay, so it always varies in the order of 10 power minus 3. So my resistivity always varies in the order of 10 power minus 3 ohm meter. Okay, sorry. Resistivity always varies in the order of 10 power minus 8 ohm meter, but there exists something called as temperature coefficient of resistivity that varies in the order of 10 power minus 3. Okay. So we learn about resistivity. So these are the list of materials which have different resistivity. Now, yes, this is for the conductors, semiconductors, and insulators. Next, we have a device called as resistor. What is a resistor, guys? Now we come to a device so called as resistor. What is a resistor? Why do we use resistor? Why do we need resistor in our day-to-day life? So resistor is a device, is a passive electronic device. Okay, passive electrical device. So what does this resistor do? So resistor blocks or controls, resistor controls the flow of electrons in a circuit. Okay, so or I can say this flow of current, can I flow of electrons, can I replace with a single word? Controls the current. Okay, the flow of electrons is nothing but the current. So resistor is a device which blocks completely or controls the flow of current in a circuit. So why should I require a resistor? Say suppose I have a 10 I have a battery here. One simple example, guys. I have a 12 volts battery. Okay, 12 volts battery with some 2 amperes of current. 2 amperes of current. Now I want to light up a LED bulb. So I have a bulb, small bulb, which requires only 20 milliamperes of current and 2 volts. Okay. Now if I connect this directly, what will happen? So if I connect this directly to this bulb, what will happen? If I connect positive and negative LEDs like this, what would happen? Yes, by resistance we can get required amount of voltage and required amount of current. Exactly, Pradeep. So bulb will burn. Okay, bulb will burn. So to control this burn, what should I do? What I'll do is I'll connect a resistor. I'll connect a resistor to control the flow of current. And when I control the flow of current, what happens when I control the flow of current? Required amount of current. I will send only the required amount of current. Okay. So resistor allows to flow only required amount of current. Okay. Only required amount of current. So it's a current controlling device. I can say resistor is a simple current limiting device. Okay, instead of controlling, I can say current limiting device. Now, this does not allow the free flow of electrons. This controls the current flowing through this conductor. When I'm controlling the current by Ohm's law, we can say V is proportional to I or I is proportional to V. When I'm controlling the current, automatically my voltage is also controlled. So say this was a simple example I could give for resistor. So there are different types of resistors available in market. So one such resistor is carbon type resistor, carbon resistors. Okay, carbon resistors. What happens here is, so inside this resistor, there will be some carbon content. So there will be carbon which conducts electricity, some metals, some conductors, metals too, some metal, powdered metal, some carbon, and adhesive, some sticky materials. So these two are mixed together in a proportion to get a required amount of resistance. Okay. Now these type of resistors, carbon resistors, are given with some color coding. So since I can't type or I can't print the exact value of resistance, so these are given with some color coding. So these are the different types of resistors which are available in our market, in our day-to-day market. So how to find the resistance of this resistors based on the color code? So for this we have a specific type always. So there are steps. Okay, steps to read a resistance. So always consider your gold. So there will be something called as gold color or silver color or no color. So you can expect 4 bands in your resistor. So there will be 4 bands in your resistor. So out of these, there are 4 bands or 3 bands. In case of no color, there will be 3 bands also. Okay. Always in your resistor, carbon type resistor, there will be gold, silver, or no color. Okay. In that case, yes, there will be resistance in the object space. So in that case, you have to keep the gold side. Wherever you have gold or silver or no color, you should keep it in the right side. Okay. Should keep it towards the right. So whenever you are reading the resistance of any given resistor, you have to keep the gold color, silver color, or no color towards right only. All other colors are left. So here is the representation of a simple resistor. So this is a carbon type resistor which has orange color in the first, brown in second, red in third, and gold in last. So always keep your gold or silver or any no color in rightmost position. Okay. So how to read the resistance? We have to keep the gold or no color or silver in rightmost position. Now, what is first color means? The first color means the first digit of the resistor. The second color means the second digit of the resistor. And third color is the multiplier. So, what is the multiplier? It's the decimal multiplier. So, it multiplies into 10. 10 power of this color. So, 10 power of x. So, first digit is first digit, the D1, I'll call it D1, second digit D2, then third digit is decimal multiplier. So whatever this particular color has any, so what are these? These colors will be assigned with some numbers. So this is a multiplier which multiplies with 10 power of this value. And then this is the last one is the tolerance, or this is nothing but the error value, error associated. So tolerance band says about the error associated with the values. It's always plus or minus of tolerance. Okay. So how you have to check the resistance? You have to multiply. So you have to take the first digit, second digit, arrange it. So first arrange the first digit, second digit. Then the third digit is the decimal multiplier. You have to multiply these two digits with this 10 power x plus or minus tolerance. This is the way you have to identify the resistance of your resistor. Okay. So how to do that? So we know there is, this is the chart for different colors. This is the color coding of resistors. What's happening here? So different colors are given with different numbers, assigned with different numbers. So for black I have 0, brown I have 1, red I have 2, orange I have 3, yellow I have 4, green I have 5, blue I have 6, violet I have 7, gray I have 8, white I have 9. For gold, it's plus or minus 5% tolerance. For silver, it's plus or minus 10% tolerance. And for no color, I will be having plus or minus 20% as tolerance. Okay. Yes, there is in every circuit wherever you see, you might find one or the other resistor like this. Okay. What is the number indicates? So number indicates the value of resistance, Hariprasad. So yeah, how to find the resistance? So how to keep, how to remember this? I hope most of you by now might be knowing how to remember those color code. So you might be given with this. So there was a person called B. Roy, who went to the Great Britain. Has okay, has doesn't have any meaning. So has very good wife, but no gold and silver. So this is the way you could remember your color codes. B.B. Roy from the Great Britain. B.B. Roy from, we can add some small phrases. So we could remember the excuse me guys. So yeah, we could remember this color code with this phrase. B.B. Roy from Great Britain has very good wife but no gold and silver. This means the black, brown, red, orange, yellow. G stands for green. So remember green. Okay. GR. Great, right? GR. GR stands for green. Blue, violet, G doesn't have any R, so it's gray. Okay. Here GR means green. Okay. Please remember, gray means green. Okay. Then yeah, G means gray. W means white. No means no color. Gold and silver. So these are the. This is the way you could remember your color code. Okay. Okay, guys, got this. So let's quickly find what is the resistance of this color code. So have orange, brown, red, and gold. So what is the value of orange, guys? Please take your fingers and to note down B, B, R, O, Y, G, E, B, W, and no color, gold, and silver. So you have use your fingers to calculate. So find out what is the value. So we know that the orange color has, so find the resistance for this given resistor. So guys, I'm waiting for you guys to answer. Please try to reply. What would be the color code? I mean, what could be the resistance of this color code? What can be the resistance of this color code? Orange, brown, red, gold. Orange, brown, red, and gold. Yes. 3, 1 into 10 power. Red is 2. So that is, yes, guys. So first digit is 3. Second digit is 1. Third digit is, as I told, it's a decimal multiplier. You have to take into 10 power whatever the color. So the color here is red. The digit is 2. Digit assigned for red is 2. So multiplier is 10 power 2. Then gold tolerance has 5% tolerance, 5%. So the resistance value can be calculated as 3 1 into 10 power 2 plus or minus 5%. Okay, this is again 3 1 into 10 power 2 plus or minus 5% or 3.1 kilo ohms. So in your when you practice more, you will be answering this in terms of this kilo ohms, mega ohms, etc. Okay, so this is its value is 3.1 into 10 power 3 or 3.31 into 10 power 2 plus or minus 5%. Okay, now guys, yeah. So its value, what does this tolerance 5% means? It's nothing but 5 by 100. So when you get the calculation, you get 0.05, right? So 0.05 means it's like 5%. Your resistance value varies by 0.05 value. Okay, it is either 31.005, 31.05, or it's 30.004, yeah, something like that. Okay, yes. So this is the way you have to calculate the resistance. Now I have a question for you guys. So four colors on the resistance are given as brown, yellow, green, and gold. So what is its resistance? What is brown, yellow, green, and gold? Yeah, please try to answer, guys. Come on, please try to answer. I think I quite launch a poll here. If you want to go answer in the poll, come on, guys. Be quick, be quick. None of the above. No, no, no. It's not none of the above. Please check that. Check that. So there is an answer. First, try to find. Okay, please try to find the resistance, Hari Prasad. That's all. Yes, exactly, Madhavi. Now try to match. Madhavi got the answer. Bhargav got the answer. At least try to give the answer, guys. Give the magnitude of answer. You get that. Okay. Yes. So no, Krishmodi, there is answer. Madhavi got it and Bhargav got it. So please note that I have modified the answer a bit. Please note that I have modified the answer a bit. Yes, Tejas, correct answer. Tejas, super. Awesome. Okay, Tejas, I given me the correct answer. So guys, yeah, we have very less time, so I'm going to in the poll and we'll discuss the answer. So Tejas had given the right answer. The answer is, say what is B? Brown. Brown stands for letter 1. mean digit 1, and yellow stands for 4. Green stands for into 10 power 5, right? Then gold stands for plus or minus 5%. So this is the answer. Now, if I take 14 into 10 power 5 plus or minus 5%, or can I rewrite this as 1.4 into 10 power 6 plus or minus 5%? So guys, you can expect some questions like these. Okay, you can expect some questions like these in your competitive exams, maybe CET, or maybe in your NEET, like if it goes easy like last time. So yeah, so here its value is the same. It's 1.4 in 10 power 6. So this is the same value, but given in a different order. That's it. So option A is the right answer, guys. So please practice those. Okay. Brown stands for 1, yellow stands for 4, green stands for 5. On practicing, you'll get this. Okay, Hari Prasad, please try to practice this. Try to by heart this. So BB Roy from the Great Britain had very good vibe. So next we are going to discuss about temperature dependence of resistivity. So what's there? So we know what happens. So in a conductor, say if we have a conductor, as we discussed earlier, there are n number of atoms inside the conductor, and there are n number of electrons. Okay, there are n number of electrons. Now, when at room temperature, what happens to this conductor? What happens to the electrons inside this conductor at room temperature? So the electrons gains enough ionization energy to move out, right? So to move out of this valence orbital, and they start to come out, right? Now, what happens if I increase the temperature? So what happens if I heat this conductor? What happens if I heat this conductor? When I heat the conductor, what happens to the atoms, molecules, etc. inside the conductor? So what am I doing? When I'm heating, I'm transferring some energy, right? Heat is a form of energy. So I'm transferring some energy to this conductor. So what happens to this atoms and electrons present inside them? There are no 6 and 5 band resistors Bhargav. Okay, so what happens to the atoms and molecules inside this conductor? So what happens is these atoms gain energy. So these atoms gain energy because of heat. So when we heat this, these atoms gain energy and they start to vibrate. Okay, so what happens? These atoms starts to vibrate. Okay, why does it vibrate? When we give heat to it, the atoms inside the electrons, sorry, inside the conductor starts to vibrate because it's gaining kinetic energy. Kinetic energy. So when I'm supplying the heat energy, the atoms are gaining kinetic energy, and these atoms starts to vibrate. So when these starts to vibrate, the electrons, there is high probability that electrons hits these atoms. The electrons can't flow freely now. They start to hit the atoms, they collide with the atoms and other electrons also. Now, with this, what happens to the resistance? So when the collision between the atoms and the electrons is more, what happens to the resistance? Will it increase or decrease? So there is no free flow of electrons now. There is lots of opposition for the electrons. So what happens? The electrons, the resistance of this conductor increases on heating. So as my temperature increases, the resistance of the conductor also increases. Why? As I explained, when I heat, the atoms gain some energy, the kinetic energy, and they start to vibrate. When they start to vibrate, there is no free flow of electrons. The electrons collide to the atoms and other electrons too. Now the resistance of the conductor increases. So how much is it increasing? So we have to check this, the temperature dependency of resistance. The resistivity of metallic conductor is approximately given as rho T is equals to rho naught into 1 plus alpha T1 minus T naught. So T is the present temperature here. T is the present temperature. So resistivity at room temperature. So rho T is the resistivity at given temperature. So whatever the temperature we have at now, at present, to that temperature, or the rho T is the temperature at which we have to find out the resistivity. And rho naught, This is the temperature at T naught. So what is T naught? At initial temperature. Or what is T naught, guys? Reference temperature. What is my reference temperature? What is my standard reference temperature? What is my standard reference temperature? We had studied this. So my standard reference temperature is 0 degree Celsius. Okay. So always remember my standard reference temperature is 0 degree Celsius. Please remember this. So then the resistivity is given by rho t is equals to rho naught into 1 plus alpha t, or this alpha t minus t naught is called as delta t, alpha delta t. Okay. So this alpha is called as the coefficient of resistivity. So what is this alpha? Alpha is called as the temperature coefficient of resistivity. We had got this equation by experimentation. Okay, where dimensions of alpha is temperature inverse. So resistivity is equals to resistivity. If you have remember, the alpha quotient of temperature is having a dimension of 1 by t. Alpha's dimension, if I want to write dimension of alpha, it's 1 by t. Okay, where t is temperature here. Okay, 1 by temperature. Okay, I'll write temperature. Actually, if I want to write the dimension formula, it's 1 by k, where the dimension of temperature is kelvins. Okay, it's given by k. Cool, guys. So dimension of alpha is temperature inverse. For metals, alpha is positive. So R is equals to rho L by A. At temperature T, my RT will be equals to rho naught into 1 plus alpha delta T. So when I increase my temperature, what happens to the length of the conductor? My length of the conductor increases by a value of alpha 1. This, guys, we had studied in our 11th in our 11th standard, where we were studying about the linear increase, the length of the conductor or length of any metal or length of any object on heating increases. Length area increases by some factor on heating. So this we had learned in our 11th class. Okay. So rho naught is equals to, sorry, then the resistance of the material at any given temperature is given by RT is equals to rho naught into 1 plus alpha delta T times of L naught into 1 plus alpha delta T by A naught into 1 plus alpha 2 alpha 1 delta T. So where alpha L, if you remember, this was the thermal coefficient of expansion. Guys, if you remember, this was a thermal coefficient of expansion for thermal coefficient of linear expansion on heating. Guys, where and beta, there was area expansion, surface area expansion for area times expansion. It was called as beta. Beta was equals to 2 times of alpha L. So this was again from your 11th standard. Okay. Guys, is there any confusion? So I think most of you are feeling bored by now. Are you? So yeah, I'll just finish this. The resistivity of any metallic conductor is given by rho t is equal to rho naught into 1 plus alpha delta t. Rho t is equal to rho naught into 1 plus alpha delta t. Where yeah, if I try to substitute the value of r, so find the value of r. R is equal to rho times of L by A. We know that. So my rho for any given temperature is given by rho naught into 1 plus alpha delta t. So I'm going to write the same. R is equal to rho naught into 1 plus alpha delta t into L naught into 1 plus alpha 1 delta t by A naught into 1 plus 2 alpha delta t. So from here, so my alpha L is very less compared to the top alpha L. The temperature coefficient of expansion or linear expansion is very less compared to the top the temperature coefficient of resistance. So my temperature coefficient of L, so this varies, alpha varies in terms of 10 power 3 minus 3, whereas my alpha L varies in terms of 10 power minus 5. Okay, so this is negligible compared to 10 power 3. So I'm going to neglect this alpha L and 2 alpha L. So I'm going to write only L naught by A naught. Then I'll write the expression for the total temperature. And the expression for resistance at given temperature is given by RT is equal to rho naught into 1 plus alpha delta T L naught by A naught. So that is given by RT is equal to naught L naught by A naught into 1 plus alpha delta T, where alpha is my temperature coefficient of resistance. Okay, so this is the expression we get. So RT is equal to R naught into 1 plus alpha delta T is the final expression for calculating the resistance of any given resistor for thermal coefficient alpha. Okay, hope you guys have understood this. So where R is the resistance at temperature T, R naught is the resistance of reference temperature T naught, and delta T is the changing temperature. Okay. At temperatures much lower than 0 degrees, the graph would go deviates considerably from the straight line. So as my temperature increases, as my temperature increases, what happens? As my temperature increases, the value of resistance also increases. This is what it shows. Okay. Next, some materials like nichrome exhibit a very weak dependence of resistivity with temperature. So these nickel iron chromium does not show much of variance with uh, does not show much of variance of resistivity with temperature. As temperature increases, its resistance remains to an extent remains linear. Okay. So like metals, the resistivity of semiconductors. So what happens to the resistivity of semiconductors? As my temperature increases, the number of thermal electrons emitted in the semiconductors will be more. So there will be decrease in resistance and there will be increase in conductance for semiconductors. So in case of semiconductors, it would be the reverse case. Okay, what happens? My conductivity is inverse with temperature. So as my temperature increases, the number of free electrons are more in semiconductors. Hence, there will be increase in conductivity and decrease in resistivity for semiconductors. Okay. So yes, how much are we doing? So we are supposed to solve these three problems, guys. Okay, guys. So that is resistivity for you. So we have three problems. I'll be attaching those problems with you guys. Okay. So is there any? Is there any confusion with the? Oh my God. Okay. Is there any confusion with thermal coefficient of conductors, guys? Resistivity, thermal coefficient of resistivity. Please let me know if you have any doubts on that. So what was happening here again? I just want to give a brief description. So when my temperature got increased, there was increase in kinetic energy of atoms. Now these kinetic energy, the increase in kinetic energy made the atoms to vibrate. So these vibration gave more, there was more resistance because of this vibration. There was no free flow of electrons. So this is the thermal temperature dependence of this is the thermal or temperature dependence of resistivity. So this temperature dependence of resistivity is known by a simple formula called ρT. That is the resistivity of metallic conductor is known by ρT is equal to naught into 1 plus alpha delta T, where alpha is called as the temperature coefficient of conductors. So R naught, rho T is any resistivity of given temperature. Rho naught is the resistivity at temperature is equal to T naught. And alpha is the temperature coefficient of resistance. Then the dimensions of alpha is nothing but temperature inverse. So alpha dimension of alpha is 1 by K. For metals, alpha is positive. The temperature coefficient is positive. So resistance is given by R is equal to rho L by A. At a temperature T, at any given temperature T, my RT resistance is given by RT is equal to naught into 1 plus alpha delta T into L naught 1 plus alpha 1 alpha L delta T by A naught into 1 plus 2 alpha L delta T. Here guys, this is my thermal coefficient of expansion, thermal coefficient of linear expansion. Okay, and this is area expansion, thermal coefficient of area expansion. This was nothing but alpha and beta, which you studied in your 11th standard. So from here, alpha L is very, very small compared to that of alpha. So that is RT is equal to naught into 1 plus alpha delta T times of L naught by A naught. So we are going to neglect these two terms of expansion. Then I'll get RT equals to rho naught L naught by E naught 1 plus alpha delta T. That is, on simplification, I'll get that is rho naught L naught by A naught is nothing but R naught, the initial resistance or resistance at standard reference. So the final resistance at given temperature RT is equals to R naught into 1 plus alpha delta T. This is the expression where RT is resistance at given temperature, R naught is room temperature, the reference temperature, and delta T is change in temperature. Okay. If any doubts in this, please let me know. Any doubts in this, please let me know. And please take your NPS. Please give the NPS, and we are good to go. So we have three problems. I will be attaching those three problems in our schedule. So Hariprasad says, why iron chrome nichrome doesn't increase the resistivity with respect to temperature? Yes, Hariprasad. So actually, what happens here is, so in general case, in any given conductor, as my temperature increases, what happens? My resistivity increases. The resistance increases and the resistivity also increases. Okay, as my temperature increases. Now, this in alloys, what happens is, so in alloys they exhibit a different way. So it exhibits some so in nickel, iron, and chromium alloy, what happens is, as my temperature increases, because of the arrangement of volume, because of the arrangement of these atoms in alloy, what happens? The resistivity, though it won't be, it won't be same as when I increase the temperature of nickel alone, its resistivity increases. When I increase the temperature of iron alone, its resistivity increases. When I increase the temperature of chromium alone, its resistivity increases. But now what happens? When I combine these nickel, iron, and chromium, their structure of arrangement will be changing in such a way that even on increasing the temperature, so even on increasing the temperature, even on increasing their what the thing. So there won't be any change in its arrangement. So there will be free flow of electrons. So the resistivity will still be linear. Okay, this is one other case. Understood? Yes, by this property. Yes, nichromes or this nichrome is used in making of magnets, and these are also used in construction of your motors. Okay, motors and many transformers, etc., are made out of using these alloys, where there will be studying about something called as eddy currents, and we'll be studying about some superconductors, etc., in our future classes. So there we'll be using these Hariprasad. Okay, any other doubts, guys? So I think Bhargav was asking for some question. So I'll go to that question. Bhargav, are you still available here? Guys, people in Zoom, please give your feedback, and you could, if you have any doubts, you could ask me, or you could leave. Guys, okay, we came to the initial thing. Bhargav, can I know which problem you had doubt on? Hi Bhargav, please let me know if you have any doubt. So, in which question did you have doubt on? Is Bhargav still here? Okay, cylinder wala. Okay, so let's check that. Okay, just a moment, I will go there. So, what was this doubt? Bhargav, what was your doubt? Okay, this problem, right? Yeah. This is a hollow cylinder, Bhargav. So what was your doubt here? Can I know what was your doubt, please? Bhargav, please let me know what was your doubt. So this is a hollow cylinder. Okay. Now what I had a cylinder which is hollow. Hollow means, say it's okay. The conductor is something like this. So if I have a cylinder, so if I have a solid cylinder, assume I have a solid cylinder and I cut a hole and I make a hole in this cylinder. It will become a hollow cylinder. Okay, Bhargav, hope you got this. So when I drill a hole through this cylinder, through this conductor, it will become a hollow cylinder. Now this hollow cylinder is a conductor. Now which part is conducting? This white shaded part is conducting. Okay, the white shaded part is conducting. Only the white shaded part will be conducting. Okay. Now the net area. What is the total area of this conductor? What is the area? The area is given by pi r square, right? So the area of cross section is pi r square only. Okay. Okay then. Okay. Okay. Is it only pi r square? There won't be any h then. Area of cylinder is okay. Yes. 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 It's pi r square L. Okay. Wait. Let me check. The area of cross section of this is pi r square. Yes, yeah, yeah, exactly. Bhargav, yes. So it's the circumference of this circle, right? Bigger circle minus smaller circle. There won't be any h. Okay, guys. Please make this correction, guys. So this was area of cylinder was the area of cross section of cylinder. Okay, we're considering area of cross section. Okay, I'll again inform this in my next class too. So please make this correction. Okay. So area of cross section is A into A big minus A small. Okay. I hope the rest of the part is understood, Bhargav. I hope rest of the part is understood by you. So I have to consider the cross-sectional area of bigger circle minus cross-sectional area of smaller circle. So pi r square is the area. So pi r square of bigger circle is 4 pi and pi r square of smaller circle is 4 pi, sorry 1 pi. So 4 pi minus 1 pi, I'll get the area net area as 3 pi. Okay, then rest is like, yeah, we can solve here. So we know that r is equals to rho L by A. So r is equals to rho times L by A. So we are going to calculate, we substitute all the values here and finally on substituting we get this answer. Okay, any doubts in this, guys, other than this? So if we take pi r square, it's instead of yeah, answer will remain the same. However, fish answer still remains the same. Okay, so you want me to solve? Okay, so 2 by 3 into 3.14 into 10 power minus 8 plus 6 is minus 2. Okay, 8 to the 6 is 6. Okay, minus 2. I'll solve this. So 2 by 3 to the 12, 4, 9.42 by 9.42. Yeah. So if you take 20 by, please take use a calculator or anything and try to solve them. Or take this as 22 by 7. We'll get 14 upon 66 into 10 power minus 2. Is it? Oh my god. Okay, wait. I'll check about this. I'll check this magnitude value and I'll let you know next class. Okay, guys. Then I have to end the class. It's being late. Bye.